Okay, so today we're going to start looking at something that waves can do that particles also can do, is that waves can reflect. Now we're going to look at light reflection. It's the easiest one to visualize, but sound can certainly reflect. It's an echo, if you will. But when we look at rays of light, they abide by a very particular kind of law. And the law basically says that the angle of the incoming light is equal to the angle of the reflected light. So whatever the angle is that the light comes in at, it leaves at the exact same angle. We usually use theta to represent the angle, and then theta prime would be the angle relative to what's called the normal. Now, the normal is a term that we would use in a math-based class, and this is not a math-based class, but normal would mean perpendicular to that surface. So if I were to zoom in on this, we can see that that light ray coming in hits the surface at that point. It reflects at that angle. We would measure those things relative to the normal line, which is the perpendicular. The law basically says that the angle of incidence is equal to the angle of reflection. How it reflects depends largely on the surface texture. So we would say the kind of reflection that we see depends on how smooth that surface is. So the ones that we want to look at first is what we call diffused reflection. So when light hits a rough surface, we're going to say that the light is diffused. It spreads out, it sort of loses order. Now again, this wave unit is all about light or waves can contain information. If I look at this parallel arrangement of light rays, that parallel arrangement of light rays contains information. It could be some image that's being created over here, and light's hitting this boundary. Now, when it hits, those surface variations may be really small, but because light itself is really, really small wavelengths, this light might scatter. We would say that it diffuses. If I have light that hits a really, really smooth surface, then it's going to maintain order. And so if this light contains information, it could be an image, it could be some data, it could be some zeros and ones, we maintain the order or the information. And so we can see images in mirrors. We can see those images because that reflected light contains the same information that we had there. This kind of light is called specular reflection. So this kind of reflection is what we call specular. You might think spectacles for glasses. And so specular reflection, the light is really smooth, or the surface is really smooth, it maintains the order. Okay, surface variations, when they are large in relation to the wavelength, we can get that light to sort of spread out. Now, I have some visuals for you, so you can sort of see this, how mirrors work and so forth. Gavin, this is going to work best if I have the lights off again. Appreciate you helping me with that. This one would take both the lights. Okay, so I have a light box, and this light box is, in this case, giving me just 3 rays of light. Those light rays are parallel to each other. And so we can, first I'm just going to show you the law of reflection. This is a mirrored surface, and so a mirrored surface is going to take light and allow it to sort of reflect, maintaining the order of the information that's contained in those light rays. So if I hit it at a very glancing blow, we can see that that light reflects at a very steep angle. If I hit it more head-on, it reflects back onto itself. Okay, and so we would again say that this is specular reflection. Now, the backside of this is also very smooth, but the surface variations are actually quite large in comparison to the wavelength of light. So that light hits it, but it doesn't really maintain order. So it just sort of diffuses off. We can see that. So that's what we call diffuse reflection. Okay. Now, we have mirrors. We have not just plain mirrors, but we could use curved mirrors. And so we don't have time in a one semester class to get into how curved mirrors operate. But if I take parallel light rays, I'm just going to do this as a showcase. If I take parallel light rays that are coming in here, I can get them to focus to a particular point. And telescopes will often use a combination of mirrors and lenses to get light to sort of focus. And so here I have parallel light rays that are coming in and then focusing to a point. Let's say I wanted to burn a hole through a sheet of paper using the sun's rays. I would use some sort of mirror like this, or perhaps a lens combination to be able to get the light to focus at that point. All of that light being focused there would make it pretty intense, and that would be sort of like a hot spot if I were to do this with like the sun's rays. I can also get those light rays to reflect and sort of spread away from each other. This could create an image, and that image would be sort of a virtual image. that would be behind that mirror. And so you look inside of a convex mirror, sort of like a mirror that you would see a shoplifting kind of mirror you see up in the corner. That would be something like this here. Okay, and so this would be a different kinds of reflections that occur. All right, diffraction. This one has an asterisk on it. This is not going to be part of any quizzes or tests, but some of you might be doing a project on your wave project that has to do with refraction or diffraction. When wave encounters an obstacle or a narrow opening to pass through it, it's going to bend around it or spread out. Subwoofers usually are very large speakers, and the reason for that is that the subwoofers are there to produce sound for low frequency sound waves, and so low frequency means large wavelength. The subwoofer frequencies are typically in the range from 20 hertz to about 800 hertz. This is the range of frequencies that a subwoofer is designed to reproduce. Tweeters are more for the higher frequency, the treble, things like that. And so the size of that speaker is all based on what we call diffraction. So how much the wave bends outward is based on the wavelength. So we would say that diffraction is wavelength dependent. The closer the wavelength is to the size of the speaker, the more it spreads. So obstacles and openings that are comparable in size are going to produce more diffraction. So if you want to listen to bass, you need a bigger speaker. And that's because it spreads out better. Okay, again, that's not going to be on any quiz or test. It's just something that would be helpful for you to know if you're doing a project on that. Refraction is our last topic that we want to look at. It is the bending or changing in direction of a waveform when it enters into a medium of a different speed. So we often will use light for refraction. Sound also refracts. It has to do with the changing of direction. Now we have a quiz coming up, and I want to see if you guys are able to interpret these things when a light source or a sound source hits a medium straight on. There's no refraction here. It's just going to change its speed. If I go from a slow medium to a fast medium, what's going to happen to the wavelength of that wave as I go from a slow to a fast medium? Tell that person that you're sitting next to, what will that wavelength do when I go to that fast medium? Tell that person. That length represents the wavelength. The speed is relatively slow. When it gets into the new medium, it's going to be traveling faster, so we're going to say that its velocity now has increased. What will happen to that wavelength when it goes from a slow to a fast medium? I think we saw it with Ellie and, I think I called him Will at the time, but Wyatt. You guys did this, right? When you had a slow and a fast medium, what happened to the wavelength when you went from a slow to a fast? The wavelength would increase. And so you would see that these waves would now get further apart. And the reason for that, again, is that it's traveling faster in this new medium. So the wavelength will increase. That, again, goes back to this concept that velocity is equal to frequency times wavelength. So if the velocity increases, then the wavelength should increase as well. That's what that's showing. The opposite would happen if I go from a fast medium to a slow medium. So now it slows down, and you should see that that wavelength would become smaller here. Now I'm not changing the direction of that wave, and that's because I'm hitting that interface straight on. If I hit that interface at an angle, this is where light will start to bend. The amount of refraction depends on two things. What is the angle at which it comes in at? That's the angle of incidence. And also, how much does the wave change its speed? So the speed is going to change from one medium to the next. So how much it bends depends on that. Depends on those two things. Okay, I want to zoom in on this one here. Notice that the wave is hitting this thing at an angle. The way I often like to look at the way that this thing will change its direction is I consider the slow medium. It's almost like this wave front here is going to lag behind when it gets into that slow medium. And so this wave would sort of fall behind on its path And so that portion's sort of been in that slow medium for longer, and it's going to drag behind. This portion would also sort of drag behind. And this one, when it gets down to this point, it would also drag behind. These things here would then sort of look like they're traveling at a different angle. And so this wave velocity that's coming in here is going to bend and start to travel at a different angle. Again, we measure those things relative to the normal. This would be my incident angle, and this would be my refracted angle. And so we can see that the ray of light sort of bends at that interface. If I were to go from a slow to a fast medium, the opposite occurs. Now what I see is that this wavefront will sort of get ahead of the other. This wavefront also getting ahead, and would see that this wave would then start to bend what we say is away from the normal. So again, which way it bends depends largely on how that speed changes. This is theta I, this would be theta sub r, and you would see that that light sort of bends. Refraction is very common for waves. Anytime that a wave would enter into a new medium, it will change its direction provided it hits that medium at an angle. Now I want to demonstrate that as well. Okay, so refraction is common for, we use lenses to demonstrate refraction for this one. And so wear glasses. Glasses rely on refraction to be able to focus light. So I'm going to take this as what's called a converging lens. And you notice what that's doing is it's taking light rays that are parallel, it's causing them to converge to a point. So this is where all of that light appears to be focused. And so that would be sort of like a bright spot. If I were to take this and try to take the sun's light and focus it to a point, all of the sun's light would be focused there, and that'd be the hot spot. So that's called a converging lens. For those of you that can see up close but not far away, so a number of people wear glasses, sometimes people wear contacts and you don't know that they have glasses. But Noah, can I pick on you for a second? Are you able to see up close but not distant? That's not what you have glasses? How about you, Nick?
No, I can't see far away yet.
Okay, so a lot of people suffer from something called myopia. Myopia is the fact that you can see close but not far. And so we use a corrective lens to be able to fix that. The kind of lens that you would have if you suffer from myopia would be a diverging lens. And what a diverging lens does is it causes the light rays to spread out some as opposed to focusing them to a point. Reading glasses, as you get older, might have a hard time reading things up close, and so reading glasses use a converging lens. And so this is more for the lenses that would correct what's called nearsightedness. You can see near but not far. So this lens would be that kind of thing. I could use lens combinations, right? I could take something like this and create, you might remember the first day or so of class, I had some telescopes out. Those telescopes were using lens combinations to be able to take light and focus those so that we could see an enlarged image. Again, in a one semester class, we don't have time to be able to go into the details on it, but that's what we call refraction. Now, I'm going to stop the video there because I'm going to have you guys do a little activity related to refraction, and that's on your Chromebook that you're going to need. And so I want to stop the video.